This is the Mercury spacecraft, designed to sustain a man in orbit and return him safely to Earth. This is the Atlas, the powerful launch vehicle that will place the spacecraft in orbit. These are the men selected to fly in the Mercury spacecraft, the astronauts. Malcolm S. Carpenter, Leroy G. Cooper, Jr., John H. Glenn, Virgil I. Grissom, Walter M. Schirra, Alan B. Shepard, Donald K. Slayton. It has become evident that full utilization of space flight requires man's ability to participate. Human intelligence and decision-making capacities are essential. Project Mercury. Its objective is to ensure safe orbital flight and recovery of a man in order to study man's capabilities in a space environment. These studies will form the basis for man's exploration of space. This is the flight plan for a normal Project Mercury orbital mission. However, if trouble develops on the pad, or early in the launch while the vehicle is still in the atmosphere, the escape rockets on the tower fire and thus propel the spacecraft away from the vehicle. Then a parachute system lowers the craft to the ground. In a normal mission, the vehicle is launched and proceeds to staging or release of the first stage vehicle engines. 15 seconds later, the escape tower is jettisoned, further reducing vehicle weight. Escape is now provided by cutoff of the vehicle sustainer engine and the normal separation system. Once the proper altitude, velocity, and angle for orbit have been achieved, the guidance system initiates engine cutoff, and the craft is separated from the launch vehicle by 3 posigrade rockets. 5 seconds later, the automatic control system turns the spacecraft around through 180 degrees and pitches it up about 35 degrees, the correct attitude for firing retro rockets in case an emergency develops. The attitude control system stabilizes the craft. 100 miles above the Earth, the craft travels 18,000 miles per hour. After 3 complete orbits around the Earth, the craft is returned to the retro-firing attitude, and the retro rockets fire. This slows the craft, allowing the Earth's gravity to pull the spacecraft out of orbit. The control system maneuvers the craft to its re-entry attitude, and the retro package is jettisoned. During re-entry, aerodynamic heating causes the heat shield to glow. 4 to 8 miles above the Earth, a drogue parachute is deployed to help stabilize the craft and slow the rate of descent. At 10,000 feet, the main parachute is deployed. A few minutes later, the spacecraft lands in the ocean. The parachute is released, and recovery aids such as dye markers and radio signals guide recovery teams to the area. Early in 1959, only 3.5 months after program initiation, design concepts for the project were firmed up, and a production contract was assigned to the McDonnell Aircraft Corporation. 2 months later, an engineering mock-up was inspected and accepted. Well over 100 wind tunnel tests were conducted on 70 models of Mercury configurations. Models ranging in size from 1% of full scale to full scale. One of the first projects was the development and testing of a heat shield to protect the spacecraft from the terrific heat encountered when entering the atmosphere. The afterbody has a double wall separated by large amounts of insulating material. Here, outer wall shingles are tested to destruction in a high-temperature supersonic wind tunnel. These are the posigrade rockets that separate the spacecraft from the launch vehicle. Component testing simulates actual conditions as closely as possible. Here, a complete Mercury spacecraft autopilot and attitude control system is tested. The table is tipped. The autopilot senses this and commands the reaction jets to return the table to the correct attitude. Escape rockets are tested. Detailed analysis shows that these rockets will pull the spacecraft clear of the launch vehicle at least a fraction of a second before a catastrophic failure on the pad or before vehicle staging. The blast from the nozzles is directed out and away from the top of the spacecraft. To take up the initial landing impact on either land or water, an air cushion was developed for the spacecraft. There is constant emphasis on reducing the risk involved in orbital flight. Every essential system is duplicated at least once to provide a backup in case one fails. As test results become known, modifications are made on the engineering mock-up. Every possible check is made to ensure that production hardware maintains the original design quality. Astronaut selection criteria have been specific. Test pilots with over 1,500 hours flying experience, past performance and engineering capabilities outstanding. The qualities always necessary in any flight research program. An academic program thoroughly informed the pilots on astronautics, space mechanics, and other aspects of space flight. The astronauts have made a great many contributions to improve the effectiveness of Project Mercury. They work closely with the engineers. Each man is assigned to a particular phase of the program, such as communications, tracking, or the launch vehicle. He keeps his fellow astronauts informed on any changes or modifications. Zero-gravity flights in aircraft prepare the astronaut for the condition of weightlessness they will encounter in orbital flight. The schedule also provides for continued proficiency in high-performance aircraft. The technical requirements and the physical and mental stresses involved in Project Mercury are similar to those confronting an experimental test pilot. The astronauts learn to tolerate the heating that may occur in case of ventilation system failure during spacecraft re-entry into the Earth's atmosphere. Every effort is made to ensure that the astronaut will be familiar with the conditions he may encounter in flight. Training for the astronauts is rigorous and comprehensive. Object: anticipate every possible flight situation. Simulate the problem realistically. Train the men to meet the situation almost automatically. One of the most important phases of the training program is readying the astronauts for the high acceleration and deceleration forces of launch and re-entry, the crushing G-loads of an emergency escape. This centrifuge produces the same forces on the same time scale as the forces the pilot may encounter in flight. The program indicates that all stresses anticipated in flight are well within the tolerance limits of the astronauts. In this simulator, the astronauts practice controlling craft attitude by manual control of pitch, roll, and yaw jets. The problem is to control the spacecraft about 3 axes with a hand control that functions best in 1 axis at a time. It takes practice and practice and practice. And then, on to a more difficult simulator for more and more experience. The entire Mercury mission can and will be run initially without a pilot. System duplication and automatic sequencing provide all necessary functions. However, a pilot in the spacecraft with manual backup controls for all primary functions greatly increases the overall system reliability. The time available to perform a task manually if automatic system failure occurs is small. The skill required for many of the manual controls is great. A thoroughly trained reflex condition pilot is the only answer. On water impact, the pilot will normally sit back and wait to be picked up by helicopter or ship. However, in an emergency, if the craft is sinking or ventilation fouled, the pilot can climb out through the top. Or, for emergency speed, blow off the side hatch. This method may be used successfully even after the craft is sunk beneath the surface. astronauts receive extensive training in sea and land survival techniques. There's always the slight chance the spacecraft may land outside the designated area. The pilot is prepared and equipped to survive while waiting for the recovery teams to reach him. Training covers every conceivable eventuality, every emergency, no matter how unlikely it is to occur. The spacecraft procedures trainer is an exact duplication of an actual flight craft. Every control and instrument functions. The trainer enables the astronaut to fly mission after mission, become completely familiar with the location and operation of every control and instrument. He learns to handle emergencies as fast as the instructor introduces them electronically. To make training more realistic, the noise background of powered flight is inserted. The pilot experiences the physical discomforts of the temperature and pressure-regulated suit, and time in the trainer is prolonged to produce fatigue. Dual microphones feeding into 3 radio systems give the pilot constant voice communication with the tracking stations as the spacecraft passes over. Oxygen, pressurization, and ventilation in both the cabin and the suit are adequate for a minimum of 28 hours. Once separated from the launch vehicle, manual backup controls provide the astronaut with the capability of controlling the craft throughout orbit, retrofiring, and recovery. In addition to reliable hardware and trained pilots, Project Mercury requires a worldwide network of tracking and control stations, manned by men thoroughly trained to do their jobs, too. The Mercury tracking range consists of 16 stations, some already in existence, others under construction. The orbit path is planned to keep the spacecraft in the Earth's temperate zones and to take maximum advantage of existing tracking stations in the re-entry and recovery areas. Planning and construction of the stations around the world proved to be a major segment of Project Mercury. The tracking stations will monitor spacecraft flight at all times, stay in continuous contact through telemetry or voice communications, exercise operational control over the mission. The training requirements for tracking station personnel are extensive due to their large numbers, their distribution all around the globe, and the need for them to operate as one worldwide network. The Project Mercury Control Center at Cape Canaveral is the nerve center for flight missions. In the training operation, trajectory data, spacecraft systems information, emergencies, all data encountered in actual flight are introduced to the monitoring consoles. Orbit predictions must be available at the instant of launch vehicle burnout, not hours or even minutes later. A complete network of communication is simulated between a spacecraft and between tracking stations. In effect, complete missions are flown again and again. The control center determines from all available data the progress of the mission. If an in-flight emergency arises, the flight can be terminated. Every effort is made to land the spacecraft in a desirable recovery area. The track board constantly indicates the position of the spacecraft and its probable landing point should emergency re-entry be initiated. In this way, recovery forces can be on the way to the landing area immediately. The next job, direct the search and recovery activities. Flight testing began early in the program to verify design concepts and check out prototype systems. Free-fall drop tests were conducted with full-scale spacecraft models. The pyramid of testing had begun. Test a component, then a subsystem, then a system. Put several systems together and test the overall capability. Keep testing until complete unmanned orbital missions have been flown. Then, you're ready. September 9th, 1959, less than 1 year from program inception, a prototype spacecraft was flight tested on an Atlas launch vehicle. It was not equipped with an escape tower since the escape system was not being tested. The objective was to match the ballistic trajectory of the craft to the re-entry path of a spacecraft coming out of orbit. The craft would then encounter the same heating environment. During this test, the spacecraft re-entered the atmosphere in a steeper angle than planned, producing higher temperatures than expected. The craft took this excessive heating extremely well. In fact, the test produced more constructive data than if it had progressed as planned. This is the nature of a space-age flight test program. At 2:19 a.m., to provide maximum daylight for search and recovery, the first Mercury rocket-boosted flight test vehicle was launched. Search and recovery teams worked smoothly. Even though the spacecraft landed outside the anticipated landing area, it was located and recovered in just under 8 hours. When orbital missions are flown, aircraft search teams and ship spacing provides normal recovery in less than 3 hours. Early in the program, a new solid propellant launch vehicle was designed, developed, and fabricated for research and development flight tests. Called Little Joe, the vehicle was used primarily to test the escape and recovery systems for the spacecraft. The first Little Joe was launched October 4th, 1959 at Wallops Island, Virginia. The test successfully demonstrated Little Joe's capabilities. November 4th, 1959. This test checked out the Mercury spacecraft escape system under the most severe conditions anticipated for a mission abort during launch. The parachute landing system operated properly, the craft was retrieved, and post-flight examination furnished the desired information. Here are the parachutes just as the astronaut will see them through his periscope. December 4th, 1959. This test simulated a high-altitude abort. Carrying a small rhesus monkey, abort was initiated at 96,000 feet, while the vehicle was traveling 5.5 times the speed of sound. During flight, the monkey was subjected to about 3 minutes of weightlessness with no ill effects. In spite of heavy seas, the craft was recovered within 2 hours after launch. All test objectives were met. January 21st, 1960. In a test of the emergency abort system under maximum airload conditions, Little Joe number 4 also carried a rhesus monkey. The flight lasted 8.5 minutes with a successful landing 10 miles offshore. The craft was picked up 4.5 minutes later by one of the Recovery Force helicopters. The research and development flight tests provide continuing training for the recovery forces in addition to verifying design concepts. Atlas launch vehicles for Project Mercury are assembled in San Diego at the Convair division of the General Dynamics Corporation. These are the launch vehicles to be used to accomplish the ultimate Mercury mission: put a manned spacecraft in orbit and return it safely. Everything possible is done to minimize the risk involved. Every part scheduled for a Mercury booster is marked or tagged with a Mercury label. 100% inspection of all parts assures the highest possible quality. System testing is exhaustive. At the Marshall Space Flight Center, Redstone vehicles undergo the same exhaustive tests and inspections after being received from Chrysler's production plant. These launch vehicles flight test production hardware. At McDonnell Aircraft in St. Louis, production spacecraft are ready. Prototype development and research and development tests have been completed. These spacecraft will ride a Redstone or an Atlas, eventually carry a man into orbit. Final assembly takes place in a super clean white room. Here too, every test and inspection possible is made to ensure reliable operation. Only 16 months after contract initiation, The first flight test of a production spacecraft involving an off-the-pad abort was entirely successful. After launch, the spacecraft escape tower combination makes a stable climb to more than 2,000 feet. At the peak of the flight, the escape tower separates, falling well clear of the spacecraft. Slow-motion photography shows the complete sequence in easy-to-follow detail. The drogue chute slows and stabilizes the craft, maintains the proper attitude for main chute deployment. The antenna canister is jettisoned, automatically deploying the main chute. No man-conceived project can guarantee 100% reliability. Yet, Project Mercury must come as close as is humanly possible. Since Project Mercury is a manned flight, the pilot must have an escape capability during the powered portion of his flight. This emergency escape system gives him that capability. The main parachute is intentionally reefed for a few seconds to reduce the opening shock, then opens to its full area. A 63-foot main chute brings the craft to an approximate 20-mile-an-hour landing, the impact cushion taking up the initial shock. The main chute is released to avoid dragging the craft, and the emergency chute is jettisoned. Within minutes after landing, a helicopter from the Mercury Recovery Forces picked up the spacecraft. In November 1960, the first Redstone boosted Mercury spacecraft was scheduled for launch. Just 2 years from program inception, production hardware was ready to fly, the result of parallel production, research, development, and training. The Redstone launch vehicle qualifies the actual hardware, the production spacecraft, the actual systems in space. In addition, the Mercury Redstone will provide training flights for the astronauts. Of course, animals and instruments will make the first flights. The vehicle will not place a spacecraft in orbit. It will boost the craft through a ballistic trajectory to recovery on the Atlantic test range. On this mission, launch was not accomplished due to premature booster engine shutoff. The spacecraft received a signal saying it was 40 miles up in space, so it began to do exactly what it was supposed to do. First, the escape rocket was jettisoned. The parachute recovery system then functioned exactly as it would on a normal flight. A month later, the same Mercury spacecraft was launched successfully and recovered. This is a Mercury-Atlas system being assembled for flight. A complete mechanical and electrical checkout follows. After static firing, the spacecraft receives a final operational check. A review board then decides whether the mission can proceed on schedule. On July 29, 1960, the first Atlas-boosted flight of a production Mercury spacecraft was attempted. This research and development effort ended after 60 seconds of flight with an unexplained breakup of the vehicle. Manned orbital flight will require more research and many more flights. On the next Mercury-Atlas flight, static firing gave notice of launch readiness. Project Mercury. The program is complex and worldwide. A successful mission, orbit a man around the Earth and bring him back safely, will be the result of a team effort. A team that involves, in addition to the National Aeronautics and Space Administration, the facilities and personnel of all the military services, United States industry, and research institutions. When the craft has been qualified in space flight, when astronauts have ridden ballistic trajectories, when everything is ready, the manned orbital mission will be flown. When this happens, a pilot will sit in a capsule like this one, on a launch vehicle like this, and start his journey into space. his periscope, he will watch the Earth recede, as in this Little Joe photography. In orbit, he will see the Earth far below. And then, he will come back to Earth safely. Project Mercury, the proving ground for man's flight into space. Leroy G. Cooper, Jr., John H. Glenn, Virgil I. Grissom, Walter M. Schirra, Alan B. Shepard, Donald K. Slayton. It has become evident that full utilization of space flight requires man's ability to participate. Human intelligence and decision-making capacities are essential. Project Mercury. Its objective is to ensure safe orbital flight and recovery of a man in order to study man's capabilities in a space environment. These studies will form the basis for man's exploration of space. This is the flight plan for a normal Project Mercury orbital mission. However, if trouble develops on the pad, or early in the launch while the vehicle is still in the atmosphere, the escape rockets on the tower fire and thus propel the spacecraft away from the vehicle. Then a parachute system lowers the craft to the ground. In a normal mission, the vehicle is launched and proceeds to staging or release of the first stage vehicle engines. 15 seconds later, the escape tower is jettisoned, further reducing vehicle weight. Escape is now provided by cutoff of the vehicle sustainer engine and the normal separation system. Once the proper altitude, velocity, and angle for orbit have been achieved, the guidance system initiates engine cutoff, and the craft is separated from the launch vehicle by 3 posigrade rockets. 5 seconds later, the automatic control system turns the spacecraft around through 180 degrees and pitches it up about 35 degrees, the correct attitude for firing retro rockets in case an emergency develops. The attitude control system stabilizes the craft. 100 miles above the Earth, the craft travels 18,000 miles per hour. After 3 complete orbits around the Earth, the craft is returned to the retro-firing attitude, and the retro rockets fire. This slows the craft, allowing the Earth's gravity to pull the spacecraft out of orbit. The control system maneuvers the craft to its re-entry attitude, and the retro package is jettisoned. During re-entry, aerodynamic heating causes the heat shield to glow. 4 to 8 miles above the Earth, a drogue parachute is deployed to help stabilize the craft and slow the rate of descent. At 10,000 feet, the main parachute is deployed. A few minutes later, the spacecraft lands in the ocean. The parachute is released, and recovery aids such as dye markers and radio signals guide recovery teams to the area. Early in 1959, only 3.5 months after program initiation, design concepts for the project were firmed up and This is the Mercury spacecraft, designed to sustain a man in orbit and return him safely to Earth. This is the Atlas, the powerful launch vehicle that will place the spacecraft in orbit. These are the men selected to fly in the Mercury spacecraft, the astronauts. Malcolm S. Carpenter,